you're going to end up with something that looks like this. And, again, I'm only using the colors for illustration. I'm not actually maintaining any colors. I'm just using it to show you that these might have come from other merge processes. Okay, now I have this graph, which has two vertices. What is the size of the min cut in this graph? Or rather, any cut in this graph? It's just the number of edges between those two vertices, right? So computing the min cut of this graph is really easy. It's just, okay, how many edges do I have? And that's my answer. So to summarize, the entire randomized algorithm looks like this. Pick an edge at random, contract the edge. Pick an edge at random, contract the edge. Keep doing this till you only have two left, report the answer. I mean, you will hopefully agree with me that this is a very simple to describe algorithm. Why it should work at all makes no sense, but it's simple to describe. Is that clear? Do we have any questions about that? Yeah.
So I have the feeling that the number of edges doesn't change because when you collapse two vertices into one, you don't lose any edges.
The assertion is that when you collapse two vertices into one, you don't lose any edges. And I see one head nodding up and down. No, I see heads going. So the axis changed.
Yeah.
Would you like to say something?
There is, when you're contracting two vertices, the edge between those two gets removed. One.
Is it one?
Minimum one.
Just one or one minimum?
Hey, ask her. I don't know.
Between those two vertices would all get reduced. If there's only one, then one. With two edges between two vertices.
Can you point to let me put this out. Can you point to an example here what might happen? You agree?
Yeah. Initially it's one, but later it could be.
Could be something. Yeah. Remember, I'm picking an edge at random. I'm not picking two vertices at random. So the fact that I'm picking an edge at random means there's always that edge. Otherwise I wouldn't have picked it. So there's at least one. Okay. So yeah, we are losing edges. Okay, good to clarify these things. Any other questions about the procedure before I start trying to argue about why it should work? Or what we hope for will happen? All good? Again, I'm not going to worry right now about the details of how you do the data structuring. Those are details that are important, but that's not what I want to focus on right now. Okay. So then the question is, why on earth should this work? So the way to ask this question is, we want to say, well, what is the probability that this algorithm at the end when it stops gives you in fact the correct min cut? Right? That's the event. The event is the algorithm stops and whatever it reports is the correct min cut. Right? And we want to know the probability of this event happening. So to ask for why this should happen, another way to ask is when it will not happen. How will this algorithm fail? So imagine the min cut. So you have this graph and you have this min cut. When would the algorithm fail?
You're removing the edges which have.
Sorry?
Which will, if you just do a normal min cut, you'll have a set of edges which will contribute to the min cut.
Yes?
If you remove those edges in random,
Yeah.
then this algorithm will fail.
Right. If you picked off one of the edges that was in the min cut, so let's imagine that we have a graph. So let's draw a graph here. So when does this algorithm fail? So imagine that I have a graph, and imagine that we could look into the future and see what the min cut was and what's these edges here. Yeah, the 5 edges here. The claim is that if we ever touched any of these edges to contract it, that would make our min cut calculation unreliable. We don't know anymore what's going to happen. We might get lucky and still somehow find an answer that we want, or we might not. But we can't be sure. So rather than saying when it will fail, let me argue when it could fail. Conversely, if I never ever touched any of these edges in my contraction, I claim what I will end up with is in fact the min cut. Because what this will go to is going to be something that looks like this. Because all the other contractions are happening elsewhere. Notice that that's the point. If I don't ever contract any of these red edges, they won't disappear. That's the only way they disappear, right? Because I contract one of them. Otherwise they'll stay. So the claim is that as long as the edges I pick to contract are not part of the min cut, then I will be okay. So if I can get all the way down to 2 vertices and never pick one of these edges, I will be fine. Okay, so now you're thinking, well, that, how unlikely is that? Come on, you've got to have enough edges in the min cut. And then you start thinking some more. I say, well, if my graph looked like this, if my min cut was 1, for example, then in fact, this is not a bad strategy. The probability of picking that one edge is really tiny. Most of them I'm going to be pretty happy. I'm going to be picking edges here, I'm going to be chugging along quite happily. I'll be fine. But if the number of edges in the min cut was really large, so if my graph, for example, looked instead like this is a good case. A bad case would be actually it's not so easy to draw a bad case. Let me think for a second. Maybe it looks like this. Right? And then I could pick, I have a good chance of picking something that's in the min cut. But remember one thing, this is not a cut, it's a min cut. If this in fact is the smallest cut, then these two sides must have a lot of edges in there. So there's some rough intuition saying, okay, look, it's the min cut I'm trying to avoid. That's the smallest possible cut. The smallest possible cut in the graph can't have that many edges in it, because it's the smallest possible cut. And what we'd like to show, and therefore there are many edges that are not in the min cut. And if you remember what I said earlier, if there's many, many things that are good for you, in our case, not in the min cut, then I could just pick one at random. So in order to start reasoning about why this algorithm might be correct, I have to say, okay, what is the probability that an edge I pick is in the min cut? Right? So let's say I run this algorithm for one step. If I can say the probability of an edge being in the min cut is something, then that 1 minus that something is my probability of success after one step. Then I have to worry about the second step. We'll worry about that next. So let's ask for the first step. Can we say something about the probability of picking an edge that is in the min cut or not in the min cut? So let's think about this. We are picking an edge from the graph, right? So we're picking one edge from all the edges in the graph. So if there are E edges in the graph, some fraction of them are the min cut edges. We'd like to, in order to figure out the probability of picking an edge from the min cut, we'd like to have some sense of how big the min cut is relative to the size of the graph. But graph could have all kinds of min cut. How do we even do this? Well, we know some things. For example, let's just write this down. So number 1, the min cut is less than equal to the degree of a vertex. Do we see why? Why is the min cut less than the degree of a vertex?
You separate the vertex down by
if I delete all the edges adjacent to a vertex, that's a cut. The min cut can't be more than that because I just disconnected the vertex. But if the min cut is less than the degree of a vertex, I didn't tell you what vertex it was. Which means the min cut is less than or equal to the min degree. Right? The smallest degree vertex has to have a higher, has to be bigger than the min cut, bigger than or equal to. Because this argument applies to any vertex. Quite problem. Okay, that's all well and good. But all we have at our disposal is an understanding of how many edges there are on the graph. How can I relate the min degree of a vertex to the number of edges in the graph? Well, here's what we do know. It's a basic fact about graphs. The sum of the degree of a vertex the sum of the degrees of vertices in a graph is twice the number of edges. Why? Because if we added the degrees of a vertex, each edge gets counted twice. It gets counted from one side, it gets counted from the other side. This is a very basic fact in graph theory. Okay, well, what does this mean? If the sum of the degrees of a vertex is twice the number of edges in a graph, then the average degree of the graph is equal to, that's just by definition, at their end vertices, the average degree is this. But then what do we also know? We know that the min degree is less than or equal to the average degree. Take a bunch of numbers, the minimum is less than the average, right? Okay, which means that the min cut is less than or equal to right? Min cut is less than min degree is less than average degree is 2e over n, therefore min cut is less than or equal to 2e over n. What does this mean about the probability of the first edge being picked being in the min cut? So imagine this picture, right? We have the collection of all edges in a bag, and there's some subset, which is the min cut. We're picking an edge at random. What's the probability it's green, given what we just discovered? Well, the probability that's green is the size of the green divided by the size of the whole set. We just said the size of the green is at most 2e over n. So the probability that a random edge, the first one we pick, belongs to the min cut is less than or equal to 2 over n. It's 2e over n divided by e. The probability that a random edge is in the min cut is less than 2 over n. 2 over n is a very small probability. So early on, the first edge we pick at random has a very small probability of being bad. It is a very high probability of being good. Right? Okay. Now here's what we want though. Let's think of the sequence of edges we pick. So let's imagine we pick a sequence of edges. We're going to pick exactly n minus 1 edges, because every edge we pick reduces the number of vertices by 1. So there's a sequence of edges, E1, E2, leading to En minus 1. Right? We want to know the probability that none of these edges, or that all of these edges, avoid the min cut. That's our goal. That's a success, right? The success is all of these edges avoid the min cut. we want to know what that probability is. Right? So what is the probability that all of EI avoid the min cut? Now here's a problem. Normally I would say, oh well, the probability that all of them avoid the min cut is the product of the probabilities that each of them avoids the min cut. Right? The probability of E1 and E2. So we can think something like, oh, the probability of E1 and E2 is equal to the probability of E1 times the probability of E2. But that's wrong. Because that's only true if these are independent factors. The problem is picking E1 changes the graph in a way that might change the probability of E2. Picking E2 changes the graph in a way that might change the probability of E3. These variables are not independent. I cannot actually separate them out and say, oh, I'll just look at the individual. So what I could have said was, okay, the probability of a random edge hitting the min cut is 2 over n. Okay, this is a product of 2 over n times 2 over n times 2 over n, or 1 minus 2 over n times 1 minus 2 over n, and life is good. But that's not true. That's only true for the first one. After that, things change. Okay? And that's a problem. But what I can say is that I can write this probability as the probability that E1 avoids the min cut. That's one event, right? And the rest, E2 to En minus 1, avoid the min cut. So think of this event as A and this event as B. So you can write this as the probability of A and B. Now we can't split this up into probability of A times probability of B, as we just said, but we can write it as the probability of A happening and the probability of B happening given that A happened. This is just a basic factor one problem. Which is good because this we just showed is 1 minus 2 over n. The probability of the first one you pick avoids the min cut. And then now we can reason about what happens to the rest of the selections given that this just happened. Given that I was able to avoid the min cut in the first step. Now this is actually very important because given that I avoid the min cut in the first step, it's a lot easier now to analyze what's going to happen. This is the same graph as before, but with one less vertex. So I can do this again. So this becomes probability of E2 times the probability of E3 to En minus 1 given E2 and E1. Now there are n minus 1 vertices in the graph. So this becomes 1 minus 2 over n times 1 minus 2 over n minus 1 times what's left. Yes?
What about if you pick an edge, but that edge also have multiple edges connected to vertices? So you count one or you count number of edges connected to vertices. So when you pick an edge, so you collapse two vertices into one, right? But in case there are many edges between those two vertices.
Good. So the question is, what happens if you have multiple edges between vertices? The answer is, I am picking an edge at random. So each of those copies has a separate chance of being picked. You think of it as a separate object. Okay? Yeah? Yes? Okay? When I analyzed my previous process by saying the average degree, that analysis does not rely on having exactly one edge between two vertices. The only fact I used was that the average degree, or the total average degree is 2e over n. As long as I count each edge between two vertices as a separate entity, which I'm doing when I sample, the analysis still works. It doesn't matter. Because think about this, right? How did I prove this property? All I said was the sum of the degrees is twice e. That's still true, even if you have multiple things going back and forth, because the degree counts all that stuff. If I have two edges, two vertices, and I have 10 edges between them, the degree of this vertex is 10. The degree of that vertex is 10. Right? So 10 plus 10 is 20, which is 2 times 10.
But then in your algorithm, if you pick just 1 out of 10, means that you don't reduce the number of vertex. Because you are still at 9.
You still, whenever you contract them. The number of vertices still reduces. I might reduce many edges in the process, but I still reduce the number of vertices by 1. Because I still have those two things, right? I take one of those edges, I contract, everything goes. And now I have these self loops.
The self loop will go when you contract to edges or?
Yeah, the self loops don't matter. They just
Should the self loops be removed because the next time you randomly pick it, there may be a chance of this within a self loop?
as long as I remove the self loops before I do the picking, the analysis still works. Right? Because I'm not picking, I don't want to pick a self loop because I'm not into contract, right? So I just remove the self loops. Now I still have another graph, it still applies. Okay, think about that for a minute. So my argument was the following. To get the first one, I did this analysis and I showed that the probability of picking an edge that's good, in other words, does not hit the min cut or avoids the min cut, is at least 1 minus 2 over n. Because the probability of it being bad is less than 2 over n. So I got that. And then by using conditional probabilities carefully, I can say, look, now that I've assumed that I avoided it the first time, I now have just another graph with 1 fewer vertex. It's going to look like this. And so on, and so on, and so on. And if you simplify this expression, this looks something like this. This looks like n minus 2 over n times n minus 3 over n minus 1 times n minus 4 over n minus 2 up to, right at the end, it will look like, let's see, this is, it'll look like, well, it's always a difference of 2, so it'll look like this. Right? At the end of I have 3 and I do a contraction and I end up doing an extra. You can also notice what's going to happen here. This will cancel this. This will cancel this, and so on, so on, so on. What you will end up with is something like 2 times 1, because that's what's left. Everything else will cancel. Divided by n times minus 1. Okay? Which is, we will say, is basically, we squint at this. This is the final probability that after n minus 2 steps of picking things, I turn this off, I don't want to you get a valid set of vertices where the min cut has not been touched. Needless to say, this probability is very, very small. It's not terrible, it's not exponentially bad, but it's bad. But we just talked about this last time. So I have this event, it's got a very small probability of happening. What should I do? How do I make it better? How would I do that in this case? So what I have is a procedure. I run it, it outputs a number, the min cut number. Right? It's an actual value for the min cut. It's a real cut. In other words, it's a correct number in the sense that it is the value of an actual cut in the graph. But the likelihood that it's the min cut is 2 over n squared. You said amplification. What does that mean here in specific? What would I do? So I have an event that outputs the best answer with probability 2 over n squared.
Repeat with avoiding the edges.
Sorry?
Repeat with avoiding the edges repeat earlier.
Repeat with what?
Like repeat the algorithm. but
Again, okay.
Again, but avoid the edges which you did earlier.
But then my analysis no longer works. It's not independent anymore. How about I just repeat the algorithm again? Not worrying about whether it did the same thing as last time. It's random anyway. What will happen if I repeat it again?
Probability decreases, but there's still a chance that.
Sorry?
The probability decreases.
Which probability decreases?
That maybe given the same value.
Think of it this way.
Definite.
Think of it this way. You're buying a lottery ticket, right? There's a 1 in, this is a very generous lottery. There's a 1 in 10 chance you'll win the prize. You'd buy another ticket, wouldn't you? If you buy another ticket, what is your chance of winning a prize? Well, it's 1 minus 9 over 10 squared, which is roughly 2 by 10, but it's not quite. So if I did this k times, right, and took the minimum of all the answers I got, right, because they're all valid cuts, right, what is the probability that the answer I get is still not the win cut? It's the probability that each of those trials fail. So let me just write this down. This is the probability of success. So the probability of failure after k trials is equal to 1 minus 2 over n squared to the k. Right? Okay. Suppose I did n squared over 2 trials. So set k equal to n squared over 2. The probability of failure is equal to 1 minus 2 over n squared to the n squared over 2. Does this start looking familiar to anyone? So if you think about you know what this is? Sorry? Log of x. There's no x. X is going to infinity. There cannot be any x in the answer. You know what this is? Oops, sorry. You know what this is? See? This is the definition. The definition of E is the limit of x going to infinity of 1 plus 1 over x to the x. Therefore, this is the definition of minus. You could just put a minus sign. So if you didn't know this, you do now. This is probably the most basic or most important thing you need to know in all of randomness for this fact, because this will appear again and again and again. The point being that if I now run this procedure, n squared over, so think of it this way, the probability of success was 2 over n squared. I ran it the reciprocal of that many times. The probability of failure now is going to be 1 over e. I don't know if you know off the top of your head what 1 over e is. It's something like 0.37. Okay, something like that, roughly speaking. This is important because now I'm saying that the probability of failure has gone from 1 minus 2 over n squared, which is really basically it's going to fail, to 0.37, which is actually a good number. I mean, such success is 0.63. That's pretty good. But now, maybe that's not good enough for me. But now that I have the probability of success being a constant, I can do the same trick again. And I can run it something like set k equal to n squared over 2 times log n. Is that another log n factor? The probability of failure is going to be e to the minus log n, because I just did it more times, which is equal to 1 over n. I've gone from a success probability of 2 over n squared to a failure probability of 1 over n just by running this repeatedly. That's it. I now have the procedure that with a success probability of 1 minus 1 over n will generate a min cut. The procedure is do n squared log n over 2 times the previous procedure. Now this of course is not very satisfying, because if a little bit of inspection will show you that this procedure by itself takes n squared time. So the overall process, because you have to look at every edge. So the overall process is going to take n to the fourth log n. That's not great either. So overall running time is equal to n squared over 2 times log n times n squared for 1. So I haven't really made as much progress as I promised you. I didn't give you this nice fast procedure. It's actually a fairly slow procedure. It's simple, but it's slow. What I will show you next time is how you can make one tiny tweak to this algorithm. A very small tweak that will bring its running time down to n squared. Actually n squared log n. Just a very small trick. And that will be next time. But before we stop, this would be a good time to sort of reflect on what we've done so far and think of some questions. And again, I'll emphasize the basic idea was design a procedure that gives you some non-zero probability of success, and then amplify. So the hardest part was coming up with that procedure that gave you that non-zero probability of success. And I should also point out that if you want this to run in polynomial time, that non-zero probability of success has to be at least 1 over polynomial. Otherwise, this trick of doing the reciprocal would require exponential time. Right? If your probability of success was 1 over 2 to the n, I need to run this 2 to the n times to get a reasonable probability of success. That's not good. So you have to get at least a 1 over polynomial probability of success. If you do that, then okay, you're at least in the polynomial time group. And that's what we got. And that's by no means obvious that this could have happened. So that first part itself was very tricky. Then the amplification is going to be easy. So just okay, so let me just stop talking and take some questions. Yeah.
All things first design algorithm and then analyze it. But coming with the algorithm, which you are supposed
Analysis? Well, in practice, it's a back and forth kind of thing. It's just like with dividing counters, like, okay, I need to use the master theorem, so I need to divide in half. How do I do that? Here it's like, okay, I need to be able to show that I'm a high probability of doing something, okay, I need something. So how you actually come up with the strategy eventually is a you know, like all things, a bit of mystery, right? But you think, okay, in this case you're thinking, I want to be able to sample somehow. Sampling means I need to have enough good witnesses of what I'm trying to sample, and then hopefully I can do something. And we've already seen one design abstraction where you say, look, as long as I can get 1 over polynomial success probability, I'm happy. That's only one thing we've learned how to do. And you'll learn more things along those lines. I mean, I will say that this was a breakthrough when it first happened. No one thought this was possible. This was a big deal. It still is a big deal. It's a beautiful algorithm, but it also means a little mysterious. It's not the most generic form of randomized algorithm, but it's very beautiful, and that's one of the reasons why we study it. So if you feel like this is magic, it is kind of a bit of magic. That's okay. I'll show you some other ones that are not so much magic, but are more straightforward. Yes.
When did this come out?
1993. David Carger, who was a PhD student at Stanford, and he came up with this thing. This was before we really fully understood the scope of what you could do. Well, I won't say that, but we were still beginning to understand the power of randomness in algorithm design. And so this one was like, whoa. Other questions while you ponder this? So take some reflection. And we'll come back to this again on Friday, so we'll talk more about this then. But again, the idea is to come up with some procedure that gives you some reasonable probability of success or some non-zero one over polynomial, and then amplify. And next time we'll see how to make this even better by designing a slightly different procedure that has a much better probability of success. Instead of 1 over n squared, it's actually 1 over log n, which means you only need to repeat it log n times to get a good probability. So that's the trick, right? Sometimes you design a better procedure that has a much higher probability of success, so when you amplify that one, it works better. And we'll see how it goes. Okay? All right. I'll see you on Friday.